Welcome to the lecture on entity relationship modeling. Entity relationship modeling is another model for organizing data into entities and relations. It takes a complementary view to the relational model we've studied before. It operates at the conceptual level and can be easily translated into our now familiar relational tables, keys, and attributes. The value of entity relationship modeling is that it provides an intuitive design approach that can be easily translated into relational schemas. This is what we'll cover today. I'll point out some differences between entity relationship modeling and the relational model as we go along. Entity relationship modeling is essentially a diagramming notation for describing relational databases. It makes a distinction between application, entities, and relationships. This helps us think about the nature of that relationship and how to implement it in a relational schema. There's several phases that we go through to get the requirements that let us build these models. The first design phase is where the database analyst meets with users of the database to understand their needs. They then represent those needs in a high-level diagram that the users can understand. They translate this into a conceptual model. So we start at a high level. The analyst chooses a data model and applies the concepts of that model to elicit the requirements of the system. The conceptual model is an overview of the enterprise being automated. Entity relationship modeling is used to represent this conceptual model. Entity relationship modeling has entities, attributes of entities, relationships between entities, and constraints between entities and relations. The purpose of an entity relationship model is to describe the data and the relationships. A fully developed conceptual schema represents the functional requirements of the enterprise. It's the types of operations or transactions that are performed on the data, and operators can be modify, search, retrieve, delete, or insert. The conceptual model is a business level model that's used to communicate with the end users of the system so they can properly give us the functional requirements. This is what we do when we develop an entity relationship model. Once we've got the conceptual model finalized, then we start developing a logical model. The logical design phase maps the conceptual design to a logical schema. Once we have that conceptual design, then we can start defining the logical structure of our tables. And then the physical design phase is the last phase, and that maps our logical design, in other words, these logical structures like tables that we've defined, into physical structures. So an important concept in entity relationship modeling is an entity. An entity is a class of persons, places, objects, events, or concepts that we need to capture and store data about. Usually it's named by a singular noun like student or instructor, as we see here. And it can be things that are persons, agency, contractor, customer, department, division, employer, instructor, student, supplier, things of that nature. Places, sales region, building, room, branch, campus, department. Objects, things like books, parts, products, raw materials, licenses, packages, tools, vehicle models, vehicles, and so on. Events can be things like awards, cancellations, flights, invoices, orders, registration, requisitions, and so on. And then concepts, accounts, blocks of time, bonds, courses, stocks. Another important concept in entity relationship modeling is relationships. A relationship is a natural business association that exists between one or more entities. The relationship represents an event that links the entities, or it's merely an affinity that exists between the entities. Advise is an association of certain instructor entities, rows or records, with certain student entities or student rows or records. In ER diagrams, we do not create this association. Instead, it's represented by diamonds. This slide is to show you intuitively what a relationship represents. However, when we translate an entity relationship model to a relational model, we're going to create a table from this relationship called advisor. And we'll see, and we can easily see what the entities are in that particular entity table. So let's take a look. So I'm going to select star from advisor. What we have in this table is a student ID matched up with an instructor ID who is an advisor for that student. So we represent that relationship as a table. We'll come back to that concept in just a few moments. It's also possible to have a recursive relationship. That's a relationship that exists between instances of the same entity. So for example, course and prerequisite. Prerequisite is a recursive relationship between course. Courses are prerequisites for other courses. So it's a relationship of an entity to itself. We can also add attributes to our entities to collect information about the relationship. This is sometimes very useful. Usually we'll be dealing with binary relationships, and that's, in other words, a relationship between two tables. Often we will have binary relationships, but occasionally we'll have ternary relationships or recursive or unary relationships. So the recursive relationship we've kind of touched on between courses and prerequisites. So prerequisite is a unary relationship. It only has one table. Courses are prerequisites for other courses. Sometimes we'll have ternary relationships, and they're usually decomposed into binary relationships, but it is occasionally the case that you get a ternary relationship. So another important concept in entity relationship modeling is attributes. An attribute is a descriptive property or characteristic of an entity. Synonyms would be things like field, property, or element. So just as a physical student can have attributes such as height, weight, data entities also have data attributes. A compound attribute is an attribute that consists of other attributes. Synonyms in different data modeling language are numerous, and they may be called composite attributes, concatenated attributes, and things of that nature. So just as an example, a multi-valued attribute is something that is possible in entity relationship modeling because it's useful for us to talk that way to business people in trying to elicit their requirements. However, as we've seen, multi-valued attributes are not allowed in relational databases. So we'll have to translate our entity relationship diagram multi-valued attribute into tables. Here's another example. Composite attributes are possible in entity relationship modeling, again, to make it easy for us to communicate with business users. However, they aren't allowed in the relational model itself, and therefore we have to come up with some rules to translate these into table structures. Cardinality is the minimum or maximum number of occurrences of one entity that may be related to a single occurrence of the other entity. So because all relationships are bidirectional, cardinality has to be defined in both directions for every relationship. So cardinality again expresses the maximum and minimum number of entity occurrences associated with one occurrence of the related entity. So for example, we might have a many-to-many relationship, something like students and courses. One student can take many courses, and one course can have many students. Likewise, we can have a one-to-many relationship. One student belongs to one department, but one department may have many students. So it's one on the student side, it's many on the student side and one on the department side. One department will have many students. On the other hand, a single student will belong to a single department. And a one-to-one may be our advisor relationship, where one instructor advises one student. So here's some examples of cardinalities between data sets A and B, or tables A and B. A one-to-one, you'll notice that each entity in table A is associated with only one record. Let me rephrase that. One record in table A is only associated with one record in table B. With a one-to-many, one record in table A can be associated with many records in table B. So one department can be related to many students. And with a many-to-many, one student in table A can be related to many courses in table B. And likewise, one course in table B can be related to many students in table A. And just a refresher on keys. A super key is a set of attributes that uniquely determines a record. A candidate key is a minimal super key. ID is a candidate key of instructor, and course ID is a candidate key of course. And then for business reasons, we select one of those to become our primary key. So here again is where we have differences between the entity relationship modeling and relational. The attribute relating one entity to another in a one-to-many relationship will not be shown in the many-side entity. The ER relationship is assumed to contain that. So, how do we denote or represent these concepts in ER diagrams? Well, an entity is represented by a rectangle, and attributes are represented by words or nouns underneath the title of that particular entity. So we have instructor and student as entities, and we have ID, name, and salary, and total credits as attributes. Diamonds represent relationships. And if we have an underlined attribute in an entity, that is the key. And we can obviously have several underlined attributes if it's a composite primary key. So we, again, when we're representing things at the conceptual level, we're discussing them with users. We can have composite, multi-valued, and derived attributes. So name might be a composite attribute consisting of first name, middle initial, and last name. Phone number might be a multi-valued. You may have work phone, home phone, and cell phone. And then age would be derived. In other words, age is actually derived from one of the attributes in the table, in this case, date of birth. So here we have the ability to add an attribute to our relationship. So we could have a relationship advised between instructor and student, and we could add date. That's the date when that advisor relationship began. We can also have roles. Roles are normally implicit because they are obvious based on the entities. For example, instructor, teaches, section. In the case of recursive roles, the roles need to be made more explicit. This is the case when the same entity is involved in both sides of the relationship. The book gives as an example the prerequisite relationship in course, having the course role and the prerequisite role. It ends up in tables that we have our course table, and then we have a separate prerequisite table that consists of a course ID and a prerequisite ID. So in the notation in the book, and there's many different notations. This is just one. So we won't become too concerned about this, but it is worth noting just for the sake of going through what's in the book and in the slides for the book. We express cardinality constraints by drawing a directed line, in other words, a line with an arrow at one end, and that signifies one on the side of the arrow. An undirected line signifies many. So we might say that we have a one-to-one relationship. A student is associated with at most one instructor via the advisor relationship. And that would be denoted like this. We have an arrow signifying 1 to student and an arrow signifying 1 to instructor. So in other words, if we take a student, they're associated over here with 1 instructor. If we take an instructor, they're associated with, over here by the student, 1 student. So let's say, you know, we show that diagram to our business users and they say, oh, well, that's actually not the way we represent our advisor relationship. In fact, it's a one-to-many relationship. An instructor may advise many students, but a student will only have 1 advisor. So we see that represented here. The advisor relationship is a diamond. The instructor and student relationships are rectangles. And in the notation of the book, on the student side, we have no directed arrow signifying many students. And on the instructor side, we have 1 instructor. So if we look at it, 1 instructor going over to the student side will have many students. 1 student going over to the instructor side will be advised by just 1 instructor. Now, let's say we showed that and they changed their mind. No, sorry, it was the other way around. A student can have many instructors as advisors, but an instructor will only have to advise 1 student. Then it would be shown like this. On the other hand, we could have a many-to-many relationship. So we show the business community one more time and they finally say, okay, we've come to a consensus now and the relationship advisor is actually a many-to-many. So we see no directed arrows here, meaning many on both sides. 1 student coming over to the instructor side can be advised by many instructors, and 1 instructor coming over to the student side can be advised by many students. And you'll see different notations, and you can certainly use those different notations if some of you have tools you're using from work. That's perfectly fine. I'm familiar with most of them, so that's not a problem. But just for consistency in our instruction, I'm going to use what's in the textbook. It's also possible to have a weak entity set. And that's something that is denoted by dotted lines under their key fields. And in the relationship, it's a double diamond. So what this means is that for section, we have section ID, semester, and year, and they will not uniquely identify a record in the section table because section is wholly dependent on a course. A section is for 1 course. So a course can have many sections in a particular semester and year, but any particular section is going to be for 1 course. So this is known as a weak entity. Section is known as a weak entity, and this is a weak entity relationship between the section and course relationships. Total participation is indicated by a double line. So a section must be part of a relationship, this section course relationship, because it is defined by a course. It couldn't be standalone. On the other hand, a partial participation, in other words, course, not all courses have to have sections. So you could have a course that hasn't been taught for a while. It's just being kept on the books in case they want to bring it back. So it's not in our database as sections. So in that case, it's a partial participation. Course does not have to participate in this section course relationship. The double lines means that section must. You cannot have a section if it's not associated with a course. We also can have ternary relationships, and it indicates the number of participants in the relationship are 3. As I mentioned, we can have, most of the time we'll have binary relationships where you have 2 entities. Sometimes we'll have unary relationships with a single entity involved in the relationship. That's also known as a recursive relationship. And very rarely we'll have a ternary relationship. There's not been one standard use of cardinality in multiple many-to-many relationships in a ternary relationship. This is not an issue with binary. You can only have one many-to-many. Some authors will indicate that each A entity is associated with a unique entity from B or C. Others say that each pair of entities A, B is associated with a unique C entity. And book authors will vary in how they define these ternary relationships. That's why it's always better to decompose a ternary relationship into binary relationships. So we're at this point going to just deal with binary relationships in the remainder of this course. So, as I noted, weak entity sets do not have a primary key because they're dependent on the strong relation they're associated with. Section is dependent on course. A primary key is what distinguishes records in a normal entity set. And the fact that weak entity sets don't have those indicates that they are a weak entity set rather than a normal entity set. And in this particular case, what we're looking at is section and course. So, in relational tables, we'll derive from the entity relationship diagram the primary key of the identifying relationship, and we'll add that to the weak set. So again, the weak entity set will have dashed underlines rather than a complete underline, indicating these are what are known as discriminators, which means that if they're paired with the primary key of the strong entity set, then they become a primary key. But by themselves, they are not. And we, of course, can take a look at that in our SQLite database. So as we translate the entity relationship model into tables, when we run into a weak entity set, we add the primary key of the strong entity set to the weak entity set, discriminators, section ID, semester, and year. That way, we now have a complete primary key for that table. And it doesn't confuse the users because they think of a section ID as identifying a particular row in the table. And we don't want to confuse them with that type of technicality. But on the other hand, we have to have a way of dealing with it. So in a weak or non-identifying relationship, the primary key of the related entity does not contain the primary key component of the primary of the parent entity. With a strong relationship, the primary key of the related entity contains a primary key component of the parent entity. And that's what we're going to go through when we transform our entity relationship diagram into tables. So we take this weak entity set here, section. We're going to take the primary key of course and add that as a field in section, and then the combination of course ID, section ID, semester, and year will uniquely identify records in the section table. Here's what the entity relationship diagram looks like for the university. I want to note several things. First, note that student and instructor do not have department name. That's because in the entity relationship diagram, that is the relationship that contains that information, instructor department and student department. When we translate this into the relational model schema that we've been using, we'll see that in fact we have some rules that tell us how to do that transformation. And we're going to cover those rules after we finish an exercise where we just practice some entity relationship modeling. So go ahead and read this set of requirements and spend about 10 minutes to come up with your version of the entity relationship model. Then when we come back, I'll go over my version of it, and we can see if there are any questions. So go ahead and start working on that. Okay, welcome back. I just kind of highlighted some of the major nouns to help myself get started with the entity relationship diagram. So let's take a look. So I have employee, dependent, department, and project as my major entities. And then they all have sets of attributes. They have, as an employee, their social security number, address, first name, middle initial, last name, gender, salary, date of birth. Department has name, ID, and locations. Project has name, ID, and location. And then we have some relationships. Dependents are dependents of an employee. They're a weak entity set. Their attributes, first name, gender, birth date, and relationship, do not uniquely identify them. It's possible, you know, they could have different names, the same name for different people. So they're a weak entity relationship with the employee entity or employee table. We also have a recursive relationship, in other words, a unary relationship, supervise. An employee is supervised by another employee. And so we define the two roles there as well. The supervisor is supervising an employee, and in turn supervised, an employee is supervised by a supervisor. So you can have many employees supervised by one supervisor, and at the same time, an employee will be supervised, hopefully, by just one supervisor, and which is the case in this set of requirements. Then we have, let's take projects next. An employee can be a member of many projects, and obviously a project may have many employees. And in addition to the ordinary things we track on projects, we also want to track how many hours an employee spends on a project. So we add hours to the relationship member of. A department will manage many projects, and a project can be cross-functional, so it may involve many departments. Let's take the relationship between employee and department. An employee can be a member of one department only, but a department may have many employees in it. On the other hand, a director is going to be a one-to-one relationship. So a department will have one director, and an employee will at most direct one department. Here we can take a look at the participation. Each department must have a supervisor. So it's a mandatory relationship, and we denote that with the double lines. On the other hand, many employees do not direct departments, only a few. So participation here in the relationship directs from employee is partial. So we have a single line there. So I think that kind of sums up the entity relationship diagram for the set of requirements we just looked at. Okay, let's next look at how we can translate an entity relationship diagram into relational tables. And that's known as reduction to relational schemas, or in other words, reduction to relational tables. So we translate an entity relationship diagram to actual database tables with the following rules. An entity becomes a table. A many-to-many relationship becomes a table with the primary keys from both tables in the relationship as fields. A one-to-many relationship in general becomes a foreign key. The primary key on the one side is added as a foreign key on the many side. So we might think of the instructor-department relationship. We take the primary key on the one side, department, and we add it as a field, department underscore name, to the many side, the instructor table. You can also represent a one-to-many relationship as a table, but it's not nearly as efficient. And so that's why you see the book representing it with foreign keys. When we look at entity sets, a weak entity set will add the primary key of the strong relationship, course ID, that will be added to the weak entity set, in this case, section. Section would not exist without course, so it is weak. Section ID does not uniquely ID a record, so we add the primary key of course ID, and the combination of course ID and section ID semester year will uniquely identify a record in the section table. With a strong entity set, the attributes are going to be the same as the attributes in the entity relationship diagram. So when we transform a many-to-many relationship, this is also known as a composite or bridge entity. And we create a table, and it's known as a composite or bridge table or entity. That's used to represent the M to N relationship. So here we've got a many-to-many relationship, and that's the one that was finally decided upon in our set of requirements for our existing university database. We take the IDs of both of the tables in the, we take the keys of both of the tables, instructor and student, in the relationship, and they become fields in the table, the composite or bridge table. And of course, because they both have the same name, ID, we have to preface them with student ID and instructor ID. And then the primary key of that table is both of those attributes combined. And of course, we can also add additional attributes like date that give additional information, but they play no role in the connective process. Here we see a one-to-many relationship, and a foreign key, it will then be added to the many side. The foreign key is a primary key of an entity that is used in another entity to identify instances of the relationship. A foreign key is a primary key of one entity that is added to or duplicated in the other entity to identify relationships. The foreign key always matches the primary key on the one side. The entity with the foreign key is called the child, and the entity with the matching primary key is called the parent. So both instructor and student have a one-to-many relationship with department. We've got department name as the primary key on the department side. So what we'll do is we'll add department name as a foreign key in student, and we'll add department name as a foreign key to instructor. And hence our schema for the relational has instructor with ID, name, salary, and department name. Likewise with student, we have ID, name, total credits, and department name. So we add the primary key from the one side as a foreign key to the many side. So again, it is possible that if you, for some efficiency reason, you think it might be better to create a table rather than a foreign key, that's certainly possible. And there are cases where if you don't have a total participation, that you may get a lot of nulls in the foreign key, and therefore, people say, well, it's just more efficient in terms of space if I make it its own separate table. But by and large, most people just leave it as a foreign key. So another thing we need to handle is composite or multi-valued attributes. Again, they're allowed in an entity relationship diagram, but not in relational databases. So with composite attributes, we just flatten them out and we take away name and we just make it first name, middle initial, last name. Same thing with address. And we'll just take out the derived attribute age and leave it to the programmers to determine age based on the date of birth field. The problem with having age as a derived attribute is it gets stale after a while. So how do we handle multi-valued attributes like phones? Well, we create a separate table for the phones, and we take the primary key of the parent table. In other words, in this case, in this example, it's instructor. So we take instructor ID, and each record is going to be instructor ID. and a phone number associated with that instructor ID. And we can have as many phone numbers associated with a particular instructor ID as we want. The combination of the two, instructor ID and phone number, uniquely identifies a row in that instructor phone table. And we would do the same sort of thing for a student. Okay, so let's go ahead and start our group project. The purpose of the group project is kind of twofold. One, it's as an icebreaker to help you guys start working together on a problem. And this will be similar to a type of thing you'll need to do in the group project. You'll have to do an entity relationship diagram, then translate that entity relationship diagram into tables in a SQLite database. So let's go ahead, get started. And of course, the other thing is just to practice with the whole idea of entity relationship modeling.